Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 29, Organic Chemistry 2. Today we will continue on chapter 7, Carboxylic acids, and we will cover the acidic and basic character of carboxylic acids. Acidity of carboxylic acids. A carboxylic acid may dissociate in water to give a proton and a carboxylate ion. The equilibrium constant Ka for this reaction is called acid dissociation constant, and pKa of most carboxylic acid is between 4 and 5. So Ka, concentration of the conjugate base carboxylates, concentration of H plus in water, over the concentration of the carboxylic acid. pKa minus log 10 Ka. When compared to inorganic acids such as HCl or sulfuric acid, carboxylic acids are extremely weak acids. But when compared to the most classes of organic compounds such as alcohols, they are relatively acidic. For example, pKa of acetic acid, CH3 in here, is around 5 pKa. For ethanol, C2H5, the pKa for this dissociation 16, which is weaker acids. Dissociation of either an acid or an alcohol involves breaking of the OH. But dissociation of carboxylic acid gives a carboxylate, and the carboxylate is a stable conjugate base due to the resonance. We have here resonance, but we don't have for this alkoxide resonance structure to stabilize it. We can see here that activation energy here is higher than this to form the carboxylate. Again, the carboxylate ion energy is less than the alkoxide using the energy diagram. Diacids, which has two acidic function, have two dissociation constant. Ka1 is the first dissociation, and Ka2 is for the second dissociation to give the dianion. The second carboxyl group is much less acidic than the first because extra energy is required to create a second negative charge close to another mutually repulsive negative charge. This repulsive effect decreases as the chain gets longer. Substituent effects. Electronegative atom enhances the strength of an acid by withdrawing electron density from the carboxylate, as we have here species electron withdrawing that will stabilize the carboxylate negative charge. This inductive effect can be quite large if one or more strongly electron withdrawing groups are present on the carbon atom. As we increase the electron density, either by group or number of the groups attached to the alpha or this carbon, that increase the acidity. For example, pKa here 4, when we have electron withdrawing group like the halo, it's more acidic. Increase the number, increase the strength of the withdrawing 1.25. When we have trichloro, we have 0.7 pKa, stronger. Consider the structure 2,3-dichloropropanoic acid. This compound has many constitutional isomers. Draw a constitutional isomer that is slightly more acidic and explain your choice. Of course, taking the Cl from the beta carbon to the alpha, make it closer to the carboxyl group, will increase the acidity. So we answer this. Draw a constitutional isomer that is slightly less acidic. Less acidic means that taking the alpha, put it on the beta, a little bit far away. Okay. Since the inductive effect is indirectly proportional to the distance, well, we get this one. Draw a constitutional isomer that is significantly at least 10 order of magnitude less acidic and explain its choice. Taking it from the carboxyl function group to alcohol function group, of course, that will decrease the acidity with more than 10 orders. Rank the compounds in order of increasing acid strength. Alpha chloro, alpha cyano, no substituent, alpha nitro, propanoic acids. Well, as we increase the strength of the electronegativity of the substituent, we increase the acidity. Okay, so the more acidic will be alpha nitro propanoic acid, then the alpha cyano, then the alpha chloro, and the least will be the propanoic acid. The stronger the electron withdrawing effect of the substituent, the greater the stabilization of the carboxylate anion. Electron withdrawing, such a nitro in the benzene ring, remove electron density from the aromatic ring and the carboxylate anion. This stabilizes the negative charge of the conjugate base, increasing the acidity of the carboxylic acid. The electron donating groups will do the reverse effect by destabilizing the carboxylate anion and decrease the acidity. Almost all ortho-substituents increase the acid strength of the benzoic acid, regardless of whether they are electron donating or electron withdrawing. This is called ortho-effect, and its cause is not completely understood. Might be a combination of both steric and electronic factors. Let's look at some pKa. NH2OH, OCH3, and CH3, all these groups are donating. See the bara 4.8, 4.7 for the meta, for the OH 4.6, 4.1, and here you have increase for the ortho, increase the acidity. It's donating, but increase the acidity. For the methyl group, here is 4.4, 4.3. It's donating, but here again also is more acidic. Okay, let's go to the chloro, bromo, and nitro. These are withdrawing groups. Okay, the bara 4 and also 2.9. 4 for brom, again also analog is 2.9. 3.4 for nitro, 2.2 for the ortho analog. Okay, that's what we call ortho effect. Salts of carboxylic acids. Salts of carboxylic acids are named simply by naming the cation, then naming the carboxylate by placing the name of the IC in the acid name by the HCE. For example, here bentanoic acid, take the IC out and replace it by ATE. So it's bentanoate, and since it's lithium, so it's lithium bentanoate. Lithium bentanoate. If you have a long chain alkyl group to this salt, sodium heptadecanoate, that's class of soap. Soap is common example of carboxylate salt consisting of soluble sodium salt of long chain fatty acids. Carboxylate salts of most other metal ions are insoluble in water. For example, when soap is used in hard water like seawater containing calcium, magnesium, or iron, the insoluble carboxylate salt precipitated out, as we call it, hard water scum. The relatively strong acidity of carboxylic acids mean that their corresponding carboxylate salt are readily made by treatment of the acid with base such as sodium hydroxide, sodium carbonate, or bicarbonates. Some purification methods take advantage of the different solubilities of acid and their salts and the miscibility of water and organic solvents, such as ether and water. And remember, if you are using this, the ether layer will be the upper, less dense than water. Also, we sometimes use chloroform, and the chloroform layer is more denser than the aqueous layer. So the chloroform will be at the bottom and the water will be the upper layer. Suppose you have just synthesized heptanoic acid from heptanol. The product is contaminated by sodium dichromate, sulfuric acid, heptanol, and possibly heptanal and its aldol condensation products. Explain how you would use acid and base extraction to purify the heptanoic acid. Well, the reaction mixture will contain heptanoic aldehyde impurities, heptanol starting material, and the oxidizing agent dichromic acid, potassium dichromate, sulfuric acid mixture. Shake the reaction mixture in water ether mixture. The ether layer will contain carboxylic acid, the aldehyde impurities, and alcohol. The aqueous layer will contain potassium dichromate and sulfuric acid. Separate the aqueous layer and have only the ether layer, which contains again carboxylic acid, aldehydes, impurities, alcohol. Then you add to this sodium hydroxide solution, aqueous solution, and shake it well. The carboxylic acid will be carboxylate and soluble in water. The heptanal intermediate, you will have some, and some react with sodium hydroxide to give the aldol condensation products, and some starting material. These two will be insoluble in water and will retain in ether, organic layer. So in this step, the ether layer will contain aldehyde impurities and alcohols. The aqueous layer will contain carboxylic acid salt. Okay? Taking the aqueous layer and acidify it with aqueous HCl, getting the acid back, extract with ether, so the acid will be in the ether layer. Okay, here it is carboxylate, here is carboxylic acid. Okay, then take the ether layer, wash it with water, and then dry the ether layer and evaporate to get pure acid. Carboxylic acids as physiological pH. Our blood is buffered at pH approximately 7.3, a value referred to as physiological pH. When dealing with buffer solution, you may recall Henderson-Hasselbalch equation, pH equal pK log concentration of conjugate base over concentration of acid. Thus, the conjugate base concentration divided by the concentration of acid will be equal 10 to the power pH minus pK. If the pH and pK are equal, means 10 to the power 0, and the concentration of the conjugate base and the acid will be equal. Now let's apply this equation to carboxylic acids as physiological pH 7.3, so that we can determine which form predominates, the carboxylic acid or the carboxylate. Recall, carboxylic acid generally have pKa value of 4 to 5. So the concentration of conjugate base over the acid will be 10 to the power 7.3 minus pKa, which is around 10 to the power 3. This means that at physiological pH, the ratio of concentrations of carboxylate and the carboxylic acid would be approximate 1000 times to 1. This is carboxylic acid will exist primarily as carboxylate salt at physiological pH. For example, pyruvic acid exists primarily as pyruvate ion at physiological pH. See you next lecture.